This is the Diamond Quantum Computer for Education. The instrument consists of 4 modules, named Control and Acquisition Module, Microwave Module, Optical Module, and Power Module. The Control and Acquisition Module generates the control pulse and get data from the detector. The Microwave Module generates the microwave pulse that matches the resonance frequency of a center. The Optical Module serves to polarize the NV spin state and detect the fluorescences. All these modules get power supply from the Power Module. To get started, we first connect the transmission line between the modules. Next, we should power the instrument and get it connected to PC. The optical base can be aligned by turning these knobs, so to optimize the polarization and collection efficiency. Inside the optical module, we can adjust the magnetic field by varying the distance between the magnet and the diamond. When the instrument is set well, we can turn to the software end. Instrument control. This part aims at teaching students how to set up the instrument, including connecting the lines and align the optical base. The waveform shows the intensity of fluorescences acquired by the PD. The low and high corresponding to the off and on of the laser. Continuous wave experiment. The purpose of continuous wave experiment is to first get the resonance frequency of NV spin. Second, show the concept of energy leaves. As you can see from the right panel, the 2 leaves indicates the transition frequency from mass equals 0 to mass equals 1 and -1 at 2.4 GHz and 2.9 GHz respectively. Rapid oscillation. Rapid oscillation shows the capability of current control over NV spin. The input parameter includes the frequency, power of microwave, and also the starting and ending time of power sequence. The higher the microwave power, the faster the spin state oscillators. The rapid oscillation also gives the time of NOT gate and half-mark gate. Spin echo. As quantum control should be accomplished within the coherence time of NV center. It's necessary to prolong the coherence time using some decoupling technique. The right panel shows the result of spin echo measurement. The peak appearance at point when tau equals T1, that's 1 microsecond. This peak indicates the recovery of coherence. T2 experiment. T2 is the spin relaxation time. The power sequence of T2 measurement is very familiar with spin echo, but varies T and tau simultaneously. The horizontal axis is the free evolution time. The vertical axis is the coherence. An exponential fitting of the measured Q will give the value of T2. Dynamical decoupling. Dynamical decoupling is a method to decouple the center spin from the environment, so that the coherence time could be longer. Here we show the zeros order dynamical decoupling, also called free induction decay. The coherence time deduced from the free indicating decay measurement is called T2 star. DG algorithm. DG algorithm is interleaved quantum algorithm for students. the result of which shows whether a function is balanced or constant. Here, we demonstrate a simplified variance of degree algorithm. The idea comes from one PRL paper. It differs the function by detecting the echo of 4 different parse sequences. The function is encoded in parse sequence. As you can see, the upward echo means the function is constant, and downward echo means the function is balanced.